Welcome back. So the next type of motion that we'd like to try to understand is rotational motion. So in some ways, rotational motion should be pretty straightforward because everything that we have done using linear motion has a direct analog with rotational motion. For example, if a ball travels 1 meter in 1 second, then its velocity is 1 meter per second. In rotational motion, if a wheel rotates 1 time per second, then its rotational velocity can be described as 1 revolution per second. We should be a little careful here because the usual units of a rotational velocity is radians per second and not revolutions per second, but they're both an angle term divided by time, just the same way that velocity is a distance traveled divided by time. Rotational velocity is labeled with the Greek letter omega, which is the Greek letter that looks like a lowercase w. There is a rotational analog of acceleration also, alpha, the angular acceleration. And this is by how much the angular velocity has changed. The same way acceleration is a measure of how much the velocity is changing. So we've doubled our fun here, basically. If we understand how acceleration is a change in the velocity over time, then the angular acceleration is a change in the angular velocity over time. However, there are a few things that are noticeably different. So one is mass. How can we think about mass in a rotating object? For rotation, there's something called a moment of inertia, which is the analog for mass in a rotating object. We're going to discuss it a lot more later. The point is that the distribution of mass, say a ring rolling down a hill, will actually roll more slowly than a ball rolling down a hill. Because more of the mass of the sphere is close to the center of rotation, so it rotates more easily, while in the ring most of the mass is far from the center of rotation, so it rotates a bit more slowly. For force, there's also an analog, so something called torque, which is the analogous to the force of an object. So the point is that many of the concepts we're using here are similar to ones that you've used before. So let's try to visualize rotation. Here we have a bicycle wheel that is rotating clockwise. First, we need to have some kind of axis of rotation. That means there's a point around which our object is rotating. Here, the axis of rotation is the axle, so the wheel is spinning around the center of it. The next thing I want you to notice is that if you are on the tire, then you are traveling a larger distance than if you are on the spokes very close to the center of the wheel. You are traveling a much smaller distance around the wheel. The circumference, so how far the object travels as it goes around a full circle, is equal to 2 pi times r, where r is the radius. So the larger the radius, the further it travels. Notice that the entire wheel is spinning at a fixed rate, a certain number of rotations per unit time. The angular velocity depends on how much of a rotation the wheel is turned. So if the wheel rotates by half a rotation per second, then the entire wheel turns at that rate. So if the radius is larger, that point moves faster. If the radius is smaller, that point moves less of a distance. But the angular velocity of the whole thing is exactly the same. If you watch the top of the wheel, the spinning object is heading to the right, while at the bottom of the wheel here, the spinning object is heading to the left. There's a lot of different motion going on here. The point is we want to simplify it by talking about how much of the rotation the wheel has performed. So we would like to be able to convert from the amount of rotation to the distance that the object has traveled. In order to do this, we want to convert the angle into units of radians. Radians correspond to the distance traveled around a circle divided by the radius. You know that the circumference of a circle, so the distance all the way around and back to the start, is 2 times pi times r. So the distance around a circle is 2 times pi times r divided by r, so 1 revolution around a circle is equal to 2 pi radians. This is also 360 degrees, so if you want, you can use 2 pi radians being equal to 360 degrees to convert from degrees to radians and vice versa. Hopefully you can sort of see why this is so useful. If you know the angle in radians, then you can multiply the radians by the radius and get the distance traveled around the circle. So if we want to know the distance traveled, then we multiply the angle in radians by the radius. Notice if we increase the radius, the distance traveled, or the arc distance increases. and if we decrease it, the arc distance traveled decreases. So we have an example to work here. So we have a wheel with a radius of 0.5 meters, and it revolves 3 times around. So the question is, how many radians has it turned? So to solve, we know that it has revolved 3 times, and 1 revolution is equal to 2 pi radians. So we just multiply 3 revolutions by 2 pi revolutions just to get 6 pi radians, or 18.85 radians. The follow-up question is, how far has a point on the edge of the wheel traveled? So we know that the radians traveled, and the radians is the arc length divided by the radius. So we can just multiply the radians traveled by the radius to get the distance. So 18.85 radians times 0.5 meters gives us that the outer edge of the wheel has turned 9.42 meters. Notice this will also work for angular velocity. If you have an angular velocity in radians per second, then you can multiply by the radius to get the linear velocity. Okay, so you have a few questions to answer here, so good luck with that, and then we're going to look at a more complex problem of this type in the next set of notes.